Hi everyone and welcome back to Codemaster, your go-to channel for mastering programming and problem solving skills. In our last video, we laid the foundation for data structures and algorithms. Today, we are taking it a step further by diving into one of the most critical concepts in DSA, which is time and space complexity and how to analyze them using big O notation. If you have ever wondered how to evaluate the performance of your code or choose the most efficient algorithm for a problem, this video is for you. Let's get started. So what is big O notation? Big O notation is a mathematical way to describe the performance of an algorithm. It gives us an estimate of how the time or space requirements of an algorithm grows as the size of the input increases. For example, imagine you are trying to find a specific book in a library. If the books are randomly arranged, you might need to check every single book. This is an example of order of n, where the time required grows linearly with the number of books. On the other hand, if the books are sorted alphabetically, you can use a more efficient approach like binary search, which allows you to find the book much faster. This is order of log n, where the time grows logarithmically as the library size increases. Big O focuses on the worst case scenario, the maximum time or space an algorithm might take, so you are prepared for the most demanding situations. Now let's talk about time complexity. Time complexity measures how the execution time of an algorithm changes as the size of the input grows. It helps us predict whether an algorithm will perform well as our data grows larger. Let's look at a few common time complexities. Order of 1. This means the algorithm's runtime doesn't depend on the input size. For example, accessing an element in an array using its index is order of 1. Next is order of n. Here, the runtime grows linearly with the input size. Imagine you are searching for an item in an unsorted list. You might have to check each element one by one. Next is order of n square. This represents quadratic time complexity, where the runtime increases exponentially with the input size. A common example is nested loops, like checking every pair of elements in an array. Let's break down order of n square with a quick example. Suppose you are trying to find duplicate elements in a list. A simple algorithm might compare every element with every other element in the list. As the input size grows, the number of comparisons grow quadratically. Next, let's explore space complexity. Space complexity refers to the amount of memory an algorithm uses as the input size grows. This includes like the memory required to store the input and additional memory used during the execution like variables, arrays or stacks. For example, if an algorithm creates a copy of the input array, the space complexity will be order of n because the space required increases linearly with the input size. Understanding space complexity is crucial, especially in environments where memory is limited like embedded systems or mobile devices. Let's review some of the most common big O notations and their meanings. Order of 1, which is constant time. The operations time remains the same regardless of input size. Example, accessing an element in an array by index. Next is order of log n, logarithmic time. The runtime increases slowly as the input size grows. Example, binary search in a sorted list. Next is order of n, which is linear time. The runtime increases proportionally with the input size. Example, iterating through an array. Next is order of n square, which is quadratic time. The runtime increases quadratically as the input size grows. Example, nested loop for pair comparisons. Next is order of 2 raised to n, exponential time. Runtime doubles with each additional input. Example, solving the Tower of Hanoi problem recursively. So to better understand these concepts, let's look at some real-world examples. So, checking if a number is even or odd using the modulo operator is order of 1, where searching for a contact in an unsorted phone book is order of n. Finding a word in a dictionary using a binary search approach is order of log n, where comparing every student in a class to find who has the same birthday is order of n square. So this is a simple example of space complexity. Just read it. Now let's discuss the time versus space trade-off. In some cases, you can reduce the time complexity of an algorithm by using more memory. For example, calculating the n Fibonacci number recursively takes order of 2 raised to n time because it recalculates values multiple times. By storing intermediate results in an array using dynamic programming, the time complexity is reduced to order of n, but the space complexity increases to order of n because of the additional memory used. So today we have covered what big O notation is and why it's important, the concepts of time complexity and space complexity with examples, common big O notations such as order of 1, order of n and order of n square, then real world application of time complexity, then the time versus space trade-off and how to balance efficiently and memory usage. Understanding this concept is essential for writing efficient and scalable code. In the next video, we will take a deeper dive into list in Python. We will explore their basics, operations and common problems you can solve with list. If you found this video helpful, don't forget to like, share and subscribe to Codemaster for more coding tutorials. I will see you in the next video. Happy coding.